Start. We are kind of 5 minutes past, and I will be coming back. So today morning we spoke about Raman spectroscopy, then spent some time understanding palm probe setups. That means you can understand how if things can be captured as a function of time. So you can do some palm probe measurement. That's what we covered today morning, that you can capture a carrier generation as a function of time. Typically spectroscopy only does as a function of frequency and wavelength, but how, so that we did that morning. But now we'll talk about another special type of spectroscopy which is becoming much more relevant in present time. Is called near field scanning electron microscopy. And just to set the things, so you are trying to image a, say, protein molecule. That's a protein, a cross like that. You take a cross section, and these dimensions are, say, between 10 nanometer around. Now, how we are going to image that one? So if you take a normal spectroscopy with light, always you have an objective lens, light comes in and you focus it, right? And typically this focal point, dimension of this focal point d is roughly proportional to lambda by 2. So you can only focus a light at that diffraction limited spot. So, and then imagine, typically that means smaller the wavelength you choose, smaller the dimension you can resolve. So small wavelengths, basically you can go to blue light, which is about, say, 400 nanometer. So we are looking at about 200 nanometer. That's it. That is the minimum features I can resolve. Means I have a two protein molecules side by side, and they are only, say, 10, 10 and 10 gaps, a 30 nanometer. And I can only resolve 200 nanometer. Think about, only up to that I can resolve. So I cannot see protein molecule with any of the optical spectroscopy we talk about. So that's problem. So anytime you have a small feature size and you want to measure it optically, you cannot. All the thing we talked about last 2 days till today morning cannot be. Even you want to do get a Raman signal from your protein molecule, and then there is sitting beside another molecule which is protein A, and this is protein B, and you shine a light with 200 nanometer minimum spot size, you have so many all mixed together. You cannot get signal only from this one or that one. You'll have all other mixed together. So that means there is a need for a different type of spectroscopy, which we call scanning scanning near field optical microscopy. So what it looks like, so this we spend time on that. This is a Michelson interferometer, right? You need to have a two beam path. One, you excite your sample with direct laser. Don't look at this one yet. Just direct laser, and then some portion of the light bounces off this mirror and creates another path. So your detector sees light coming this way and light coming this way, so, and create interference pattern. We've gone through that process, that we have a correlated signal and the Fourier transform to get the wavelength dependent absorption or reflection. That's what we did in FTIR. So that is very common technique we understood. But now we will actually, instead of illuminating the sample with light, we illuminate a tip. So what it is a AFM tip, kind of some kind of cantilever, a sharp tip. So I focus the light, that's my sample. Before, always I focus the light here to get my signal out. Here I will focus the light onto the tip. So that's my light, and this tip dimension could be tens of a nanometer. That's the difference, and we will show in a minute how that's going to change our measurement. So again, that was the point I was alluding, that we are kind of limited by lambda by 2 diffraction limit. That's below that we cannot resolve. We cannot resolve spatially, means something changes in the xy plane, we cannot measure because of the diffraction limit. So what we will be doing in this near field mapping, that we will be having a tip and we illuminate the tip with this incident light. So that's my illumination, and we're looking, say this is an example I put called antenna, just simply a metal piece which is sub wavelength, like maybe 10, 20 nanometer in the lateral dimension, and illuminate that. So now what's going to happen, before we go to the next slide, so what's going to happen fundamentally, that now just we take an example of a small metal. So we have a small metal strip, a narrow patch, and now we are having this tip, and we are illuminating that tip with the light. So what's going to happen if you take a cross-sectional view, this is my metal, this piece, and when you illuminate with light, you create the near field, because that's how you excite the plasmon, right? So you excite your plasmon, your fields are like this, you create a strong near field. So your near fields are like that. Now if you take a little better picture of the, so you have this, that's your thing you want to image, and you excite with your light, and you create this strong near field. You create a strong this electric field in between the tip and your this, say in this case a gold pattern. This is your gold pattern. You create this excited surface plasmon, you create this field, and this near field are perpendicular to the metal surface. So what's going to happen now, you create a dipole here, because as soon as you have a charged oscillation, your charge are now oscillating on the tip. So now anytime charge oscillate, as we spoke today morning for the Raman, that you create a scattered light. So light now scattering from your tip. So this is the, now I will only look, the next slide will talk about that. We will only image or measure the light which is scattering back. So this is the light I will capture. So if I can capture the light which is scattering back, that means I am only capturing light which is coming from this small volume. So now this volume can be tens of a nanometer. So I create a situation that I bring a metal tip and excite that tip with a laser, and the tip is in the very vicinity of the near field, means the light actually illuminating the tip as well as the whole thing. This is the whole system. And now as soon as you illuminate the tip with the light, you create a strong near field. That is because the tip is very sharp, right? If you study any time a plasmon, this is the electron density is much higher. So you excite a strong surface plasmon on the tip. So you create this plasmon where electrons are bouncing back and forth, back and forth, back and forth. So now your incident photon getting re-radiated, means because now this oscillation of the dipole here is the same frequency of your incident light. That's your incident light. So it is oscillating at the same, because this is driven by the same E field, right? So whatever your E field frequency, which is my incident light frequency, this dipole, because this dipole only driven by this electric field, so it is oscillating at the same frequency of your incident field. So I create a re-radiated photon out of that, and I measure only that, and illuminate is show that that's what we measure. That means now I'm only collecting signal from this volume, nothing beyond that. So if I can map that thing again, just to go back in a more detailed fraction. So this is a setup where we are looking at that my laser beam, and again we saw that we need a beam splitter to make 50% photon go to a mirror for this Michelson interferometer, right? If you are there in the first day, if you are not on the first day, then I think we are not talking on the same page, and it will be very difficult to go back to the first day talk. But you can see that 50% light goes through and hitting the tip, and then the tip rescattered the light back, and that comes back through and interfering with your another 50%. So you are now collecting your detector getting 50% from this and 50% from this light, and then we'll do Fourier transformation. So the point here is that now you are resolving the space with the tip dimension, which is 10 nanometer in this case. So now you are actually collecting your signal from a really small volume. Previously, we only use a optical objective lens. This is the previous arrangement, no tip. This is my lens, and it focused the beam here, and you are collecting everything back. So if you don't have the tip, you are simply normal spectroscopy you are doing, and your resolution means from where you collected signal is only limited by the dimension lambda by 2, limited by the diffraction of your lens, which is always lambda by 2. We cannot defeat the diffraction from any object. But now we are not collecting the light directly from which we're focusing through that. We're only collecting the light coming from the tip. So that allows us to collect the signal from a very small, narrow area. So we could go to less than say 10 nanometer resolution, and rest of the other part remains same. This is same Michelson interferometer. We are simply collecting through the autocorrelated signal, and the computer will do the FFT, and it will plot the lambda versus amplitude plot. But now I am actually seeing a very tiny spot. Okay, collecting. So you're looking. So basically, you're collecting a signal from say a protein molecule. Otherwise, you cannot, because proteins are much smaller. Say for instance, compared to. So that's kind of what I was mentioning with my little picture. That's a tip, is a metallic tip. When you excite with a light, you create a kind of dipole oscillation on the tip, and that's the very common dipole. Your polarizability, you're polarizing the tip, means you're moving some charges across. That's your polarized. So you're kind of moving the charges across the metallic tip, and then that's proportional to incident field. So that's your polarizability of the tip. It is kind of very basic electromagnetism, that you're polarizing the tip with incident field with the polarizability of the tip. So you choose the metal and the dimension that will determine how much it will be polarized. So each time you are creating charge oscillation, you are re-radiating the photon backs. So you are actually re-radiating things only from this near field. So you could actually map much smaller dimension compared to a normal lens-based approach, where you can only collect signal from about lambda by 2. We indicate about 200 nanometer ballpark minimum. Beyond that, there is not many sources which can go less than that. So we're talking about hundreds of nanometer versus tens of a nanometer. Again, now this is just go back to a little bit of electromagnetism, that your incident field creates a near field. That is always, you have incident field, and you are trapping light between a metal piece and your material. This is a simply antenna, but it could be your protein molecule. And so you are trapping light because you are exciting a strong near field on the edge of the metal. Always metal, because of the lightning rod effect, it has a more electron density, means number of electron divided by area is a density. So electron density is much higher. So you create a strong plasma, and strong plasma creates strong electric field. That is, so your field here, total field, is the incident field, and then the field you produced because of the tip, the sharp tip. And then for normal tip, polarizability is a kind of diagonal matrix. So most cases you may not have a crop, means x depend on x, y depend on y, and z depend on z. So you can have a component, means if you excite with x dimension polarized light, y dimension, or out of plane z dimension, that comes from its polarizability. So again, that's kind of, you can see, if you don't, I never did a polarizability study, you can understand that you can create an electric field we call polarizability, which is proportionate to the incident field. Makes sense, right? More field I give here, more field polar, means more far away the charges. Basically, this is basic going back on normal electrostatics, that you have a piece of material, you apply electric field, and charges will be driven by the field. So you create positive charge, you create negative charge, and that's your dipole moment. So this is separation is your D, and the dipole moment dm is q times your distance d, and that is proportional to dipole moment, which is actually called it polarizability, is proportional to E field. So more field you give, it gets more separated. That's kind of the way. So polarizability coming. So you make a polarized, and then you actually kind of more field intense laser beam you give, you make the this tip more polarized, and we will see in a minute that more you do that, then you actually create more scattered field. And you can see the tip has a xy asymmetry, means it is not symmetric in the x and the y plane. So what I'm trying to say, with going to the too much of a math, I'm trying to say that you are creating a two polarization component. One is S and P. It makes sense, right? I am illuminating the tip with a random direction, with a direction which is not aligned to x and y. So that means my scattered photon also will have a S component and also have a P component. That's what I'm trying to say. So you actually can measure the signal as a function of S and P polarized. So you actually capture S and P polarized signal out of it. So that's again same thing, kind of retain that even detector sensitivity plays a role. Makes sense that you generate a field and detector also has to sense it. So kind of normalize with detector sensitivity and kind of Rashi. That's kind of same. Keep writing to find out the ultimate field I'm looking at. So ultimate scattered field is the you are looking at is the incident with respect to the incident field, because I'm kind of illuminating. I'm illuminating with the incident light, and just a nutshell that I'm trying to find out how much S polarized light I am collecting back with respect to the total incident field, and how much P polarized light I am collecting with respect to the total incident light. So that's the light I am, my scattered light I am looking at. So again, just going back to the same polarizability analysis, that you multiply, you are driving your polarizability in the XYZ. It is not a only X dimension or any one dimension. So it has a component into the X, Y, and Z direction. So your polarizability can be written alpha X EX, alpha Y UY, and alpha Z EZ, because it is a vector in three-dimensional space. So you create your S polarized light, which has a component into the X, Y, and Z, because it is a three-dimensional entity, a tip. So it has a X, Y, and Z component. That's what we're kind of breaking into three component, and that's our P. And the P actually also has a Z component. So you have a X, Y, and a Z component. So if you can go back and follow the steps like that, let's not bother. So ultimately the point I'm trying to say, the Z P polarized light is only depends. So P polarized light means a light which is coming with this polarization, my S polarization, that's my plane of incidence, parallel to the S polarization, and light scattering back with this polarization is my P polarized light. So I'm talking about, I think very difficult to imagine the equations. Just for normal, I'm sending a light in this plenum, so that's my tip. I'm illuminating with like that. That's my tip. I'm illuminating like that. And the lights are scattering from the tip. So it will scatter with a polarization parallel to the in plane, means a polarization vector will be parallel to this plane, which is my S polarized, and some light will come as a perpendicular polarization to the plane of incidence. That's my P polarized. So I will measure with a polarizer, I will measure a polarization vector in this plane and a polarization vector that plane. And that's the two polarized light I just measured. So again, that's kind of a little math to explain, but you can imagine that that's how light does and everything, that it has can divide into two component, and then we can monitor that. So why it now becomes so relevant? This is actually very new. Within we're talking about within a 5-6 years, the field kind of emerging a big time, because now people started looking at how plasmon propagates. They are looking at how polymer chain reaction takes place. Lots of protein folding, protein formation people are monitoring, which previously nobody could see it because of the light doesn't allow. A lot of semiconductor defects and carbon nanotubes, two-dimensional material like graphene, all could be imaged. A lot of nanowire can be seen now because they are tens of nanometer dimensions. So that kind of opened up a possibility of seeing many things which we couldn't see before. Just to see some example, and again similar type of setup, we saw it many times, two path Michelson interferometer, and then instead of just focusing the beam, you focus to the tip. That's a tip enhanced measurement, and then you see lots of features, like this is a metallic meta surface from metamaterial guys who make these meta molecules, and you can actually see the fields at a much smaller dimension, like 300-400 now, and slowly we'll go to much smaller. So this is more of a single nanowire. So people could now can see a single nanowire. So we're looking at a less than a hundreds of a nanometer now. We are looking at through this kind of tip enhanced. So you are focusing the beam on the tip, and you scatter the light, which is now interacting with your nanotube and returning back. So you're imaging through that process and seeing those tips, those nanowire, which you cannot see through normal optical spectroscopy.
So you need a special
Tip, pressure wavelength, pressure wavelength, wavelength.
no, treatment of the sample for putting in this technique.
You need what?
You need to create a special antenne with the sample.
Sample need not be too special. Like people just spin coat a nanowire on a substrate and you just scan through. As long as your AFM tip can scan through, that's okay. As long as you don't scratch the. So there is a good point that there's a little physics involved that you have to kind of make sure how far it is. You don't want to touch it. You want to be called tapping mode. There are many modes you can do AFM. Either you call tapping mode means you are scanning the surface, but with a tapping means you're tapping continuously with small gap in it. You want to make sure there is a small gap in it, because that's how you are confining the local near field of that. Because you are trying to now again, let's just to revisit the point. In case I missed it, your ultimate plan that you want to. So this is my normal lens dust. Is focus, and I measure everything in that. That's my normal lens dust. I'm saying that now I bring a tip, very sharp tip, and it creates this near field. This is my near field. I want to use that to image, to see everything. So I have a surface. I want to see everything using that field. Previously, this is hundreds of a nanometer, 200 nanometer. This is tenths of a nanometer. So I'm seeing, collecting signal only. This come as soon as it touches your surface, you scatter the photons. So that's what kind of we're doing. So for that you need to, again, this is a kind of a precise control of the software and the knowledge how low you want to go before you start scanning. That's kind of, and you can see that more farther away you go, your signal amplitude goes down. So, and as soon as you touch it, again you go down. So you have to maintain tenths of a nanometer, because if you go more than 20, 30 nanometer, typically a near field stretches from the tip about 50 nanometer. So you want to be within that range of scanning. So again, so you can actually scan it and then generate, just to show some of the kind of people try to measure at very small dimensions. This is a nice one actually. I think it appeared both into Nature where they could show propagation of plasmon on graphene sheets. That's kind of nice. So you can excite the plasmon using the tip, and you can now tip can be scanned, right? You can collect signal as a function of XY position. So you collect and you map the plasmon propagation. So you excite graphene plasmon. So yesterday I was talking about our graphene detector. So that's your monolayer graphene, and you bring your sharp tip close by and you excite with a laser and you create this near field. A strong near field you create, and this near field get coupled to the graphene and they try to propagate. So what you do, that you scan your tip across in the XY plane, and you create the map of the plasmon propagation. So you can actually see how plasmon propagate, the waves propagates as a function of XY plane. No Z, because kind of we are scanning in the XY plane. So you can actually see because of the sharp tip. So again, people went back and that is become a routine now to measure, say, many defects on a graphene type of two-dimensional material. So where really imaging is a problem of a two-dimensional material because of their thicknesses and the flecks are and sometimes they're flaky, makes very small, tiny flecks and not easy to measure them. But now with this kind of ability, you can actually really scan a graphene and you can see the grain boundaries. So these are the grain boundaries, means that's how the material changes as a function of XYZ plane. So you scan the tip in the raster scan, and at each location you collect the signal and you create a 2D map. So you can see the grains and the defects, so many information which you cannot get, normal imaging will not give you. Normal imaging in minimum will resolve 200 nanometer, which is huge compared to the thing we're looking at a two-dimensional plane. So that's kind of opens up a new avenue for imaging. So people do all kinds of imaging, and then you can also understand that this imaging also is a function of wavelength. So you can actually go down or go up because you want to excite something. So many times the thing we are working on, I spoke yesterday about our graphene-based infrared detector and camera development. We're into 10 micron band. So for us, we need a laser at around 10 microns, something like that, 9.6 microns. So you can actually change the excitation laser wavelength and get a completely different imaging out of it. So that's kind of shows that a lot of meta structure people could actually kind of capture, which other will all sub diffraction limited structures, which is not be able to resolve as a function of normal optical spectroscopy. So that kind of brings us back to a point that you can now rest part, the signal part, you can do, we did that day one, that you can use this Michelson interferometer to improve your signal to noise ratio, because here this is more of a direct measurement. So I just missed the point. Here you see that this is not a interferometer. You just scatter the light and you measure the light directly, which will have a lot of issue with the signal because you're not creating enough scattered photon to have a good imaging. So that things you have to do is a Fourier transform near field microscopy, which becomes very expensive. So this whole thing costs about $600,000. So I'm kind of myself behind buying it. A company in Germany called Niaspec, they started, and as soon as they started 2 years ago, each big university, I think now I know Harvard and Stanford and Caltech, they're all trying to buy, and I myself trying to buy, but 600,000 is still 600,000 US dollar. So the point is that now a Michelson interferometer into it, so you do interferogram, same thing, you instead of directly taking infrared light coming to a sample, you take the scattered photon and that makes the interferogram, which we did day one, and then do the FFT to get the spectrum back. So that gives you much more high signal to noise ratio. And then the key point here is that you can also change the source. You can actually change your laser source, and you can have a wavelength dependent. Now your source, this is ABC, you are exciting with 3 different lasers and creating a spectrum. So you actually create a spectrum not just based on one laser excitation, but with a multiple laser excitation, and create a more complex hyperspectral imaging. So each one wavelength excitation has various means your material may not be responsive enough for one wavelength, but could be responsive to the other wavelength. So you can actually decode, means you may have some mixed sample which may be only be excited with lambda 1, but lambda 2 may not excite the other mode. So you can actually do all kinds of but again, this is a very new field. I'm pretty sure not people still didn't figure it out how to really get information out of it. Like so it's kind of a near field, and then also you are doing this multispectral excitation with lasers. So it kind of makes things even. So now want to make it even difficult. That is the ultimate goal, and I think John was asking that today morning we spoke about pump probe setup with ultrafast techniques, so that especially we want to, we did that before, that we excite with a pump and you create a carrier here. It means you change the property of your sample because you excite. Then you bring a probe with some delay and measure it. So now question is, can we do pump probe, tip and FTIR all mixed together? So now I can temporally resolve it. I know as a function of time because I'm probing through the probe. Again, today morning we spoke about the pump probe setup. If few of them are here, so understand what I'm meaning. So you can do a time dependent measurement. We can do a tip enhanced measurement because I'm collecting signal with 10 nanometer resolution. Plus I am doing FTIR so that I can actually do much accurate frequency resolution. So I can create a spectrum coming from 10 nanometer and also as a function of very short time. So I can actually create a spectrum as a function of time. Ultra fast time could be a femtosecond time scale. So I create each 1 femtosecond I can create a new spectrum. So I can understand how material is changing as a function of time. Make sense, John? I think you asked this question. That is the ultimate setup behind. I'm hopefully by November, so I'm still working through the almost crying at a level of going to program manager's office or almost crying to Washington DC that I need that to really, this is the way to see how molecule evolve or how carrier change as a function of time and as a very small location. So I can resolve spatially with 10 nanometer resolution, temporally with a femtosecond, and as a function of many wavelength. That is a killer thing to do. So that's what it is, ultra fast S norm. So you can actually bring a pump as a wavelength so that you create your some phenomena, say you generate some carrier at a femtosecond time scale, and you do only over a very small area because of the presence of the tip, over only tens of a nanometer area, and send everything back to Fourier transform to get a more frequency resolution. So you have a frequency resolution, you have a temporal resolution due to the pump probe, frequency resolution due to the Michelson interferometer based FTIR, and temporal and spatial resolution because of the tip enhanced. So you actually can really see a molecule, how it changes as a time and space and frequency. That's the ultimate. It's very state of, we are talking about a year time. The whole world, this is the last year spectroscopy. So everybody now trying to behind it, but it's a complicated and super expensive thing we're talking about. We're talking about total $1 million setup just to all aspect. Yeah, I'm still crying. Each 2 months I go to Washington DC like a small, believe me or not, that's the US problem is like there are so many successful guys that we go and like a begging bowl and cry to the program manager, almost cry, and sometimes they throw us back. Like sometimes I still remember standing there, he said, why are you still standing? I'm still busy, I have to go for a meeting. He feels so humiliating that I'm like a beggar asking for them. But he knows that people like us always want to understand something better. So that's what kind of we are, and I'll talk in a minute about our infrared detector part in 20 minutes, which yesterday I promised we did the half part, and today I'll finish that and I'll show you why this is important so that you'll get a context that some application need spatial, temporal, and frequency information, all three. So that kind of ends my spectroscopy part up. So is there any question? We can continue talk about it. But as I promised to end yesterday's our new class of detector. So again, I will just quickly scan through, not everybody was present. So we wanted to make a infrared detector based on graphene. That was the plan. Just I'll zoom past because that yesterday we covered. So, but graphene has no band gap. We cannot form a PN junction, so we cannot separate carriers. And graphene is only one atomic layer thick. It doesn't absorb light. So we can, again, that's what it looked like, doesn't absorb all across light spectrum, less than 2%. So that's kind of a, just kind of jump ahead because I think I covered yesterday. So the plan is to kind of do some engineering to pattern the graphene on top and then excite some cavity mode. And we showed that even in one layer, just one atom, 0.4 nanometer thick, we can absorb about 60% of 10 micron photon. So the huge photon, 10 micron is a huge wavelength compared to 0.4 nanometer. So I'm absorbing a huge long wavelength photon only in a 0.4 nanometer. That's what kind of that's why just this we talked about yesterday, and that's kind of we showed we can pattern graphene, grow graphene, and experimentally measure. We can go to 50% absorption, and also we can dynamically tune the Fermi level. Means we can change the number of carriers on the graphene because it is a tunable material because of this band dispersion, band diagram. We can apply a voltage. And again, today morning, yesterday I spoke about graphene Raman spectrum, but didn't cover Raman. So today we covered the whole basics about the Raman. So this is a Raman spectrum of graphene, pristine, nothing on it, and then pattern, because we have to pattern to create some plasmon on the graphene. And we kind of showed that even with the patterning, graphene doesn't lose any of the properties. It remains exact same graphene. So that's also needed, because if you pattern graphene with this kind of 300 nanometer period, 100 nanometer diameter pattern, you are worried that we may lose electronic property of graphene, but it's reconfirmed through Raman. And today morning we spoke about the Raman comes to a vibrational resonances of graphene carbon atoms. So it's basically very pristine information about the bond. So bonds and everything remain same, and that kind of proves that. And kind of today morning we went over Raman. So now the question is, I just have to kind of pass through, then eventually showed you can go to 60%. And yesterday, again, just to show experimentally, we could go to, so again, it's one of the, nobody in the world ever showed that a graphene can absorb 60% of light. That's kind of our kind of name in that you could kind of engineer that, showed that absorption is quite angle independent, because our goal is to make a detector out of it so that I can see a big, you take infrared image picture, you want to not only take a normal, I just don't want to see you only normal angle, but even from another angle I can take a picture. So that's to show that is quite broad angle that the absorption remain invariant. So that kind of brought us back, again, this kind of some of the thing I'll just scan through, not that important at this moment. So now brings us back to an important point. Okay, now I absorb a photon on graphene. So you absorb a photon, now what's going to happen? So now if you look at that, we are treating graphene as a semi-metal. Again, just to remind us back what we are talking, so that everybody gets something out of it. So if it is a semiconductor, should have a band gap, right? So you excite with a light, and you makes the electron go to higher energy state, and you make a bias in such a way that electron goes this way, hole goes this way, and that's how each photon comes in, you create electron. That's your photodetector. But now in our graphene, it has no band gap. This is band, valence band touches the conduction band. Means if you apply a voltage, it always carries current. You cannot stop current flowing through it. So it is kind of a semi-metal. So, and then you can actually semi-metal. So now you excite the plasma on the electron, on the graphene, because it has a lot of free electron, because it is semi-metal. So now at the tens to hundreds of a femtosecond time scale, you kind of Landau damping, means you re-radiate some of the photon back because you excite carrier. Some of the carriers will re-radiate, because we spoke all the time, and as soon as carrier or electron moves, it re-radiates photons back. So we'll have some re-radiation called Landau damping. Then at a hundreds of a picosecond, 1 to picosecond time scale, you actually create hot carrier. Means the electrons absorb photons, and they are high energetic. They are jumping onto the graphene film, because now you call it hot carrier. So you create some hot carrier on the graphene, because now they absorb the photon because of the thing we spoke about yesterday, that we excite some surface plasma on the graphene, and you create those hot carriers on the graphene. And then eventually, if you don't do anything, those hot carrier thermalizes. So eventually, you actually hot carrier get balanced out, because they lose energy after scattering with each other, scattering with the lattice. Eventually, they thermalizes. Like that is of the nature. Universe like that. We get all excited about on something, but even you get a lottery. Say for instance, you get very excited about, but after a few days, you spend money, and slowly you kind of normalizes. That's any excitement goes eventually down. So that's the same phenomena looking at they were exciting carriers, and then they eventually. So our point is that before it does it, we have to do something. This means we are in carrier. So we absorb a photon and do nothing about it except heating it up. This is a heating process. You are absorbing a photon and making temperature increase. So you are just heating it up. So what is the point of heating up a graphene with light, which is not a very exciting thing? We cannot get anything out of it. So, so what we did, we found a, I think, interesting way of doing the business here. So we make the graphene. I think if you pay attention, you will understand that we made a graphene film between source and drain, and we pattern a half area of the graphene. So 50% of the area is pattern. So now this 50% area will absorb about 60% of the light, and the unpatterned area of graphene, which is the inherent graphene or pristine graphene, will absorb only 2% of light. So now you have a 60% of light absorption, 2% of light absorption. So you create a lot of hot, 60% hot carrier here and almost no hot carrier there. So as soon as you do so, you create temperature gradient, right? Because of the strong absorption at the source end versus the drain end. And as soon as you do so, you create a thermoelectric. You all understand thermoelectric. You take a piece of material, you heat one side and keep cold other side, you create a voltage called thermoelectric voltage. So as soon as we did so, we create a thermoelectric voltage across the source and drain. So now we have a graphene. I patterned and do all the optics, which we covered yesterday with the cavity and all these things. So you can create an absorption strongly on one side and weakly on the other side and create a thermoelectric voltage. So that's now brings us into a technique that each time light comes in, I create a voltage out. Because I couldn't follow the normal photodetector scheme using graphene because it has no band gap. I create, so now if you're still thinking about it, what it is, so now for a graphene, it looks like this is a band structure. So that's the band structure. So I am absorbing only intraband because interband absorption is huge. Maybe in X-ray, we cannot do intraband, interband. We are doing this intraband transition, means your photon comes in, h nu, your carrier goes only from here to here. Your electron jump here to here. But now the energy gap between them is so small that they recombine quickly. So that means even if I on a graphene sheet, even if I send photons and say absorb 60% of the light, but they recombine, they create carrier momentarily, but they recombine quickly because of their energy gap is very small. For normal semiconductor, it's a band gap. You create the energy electron here and hole here, and even their same location, the huge energy barrier, they cannot recombine. Like you standing on a railway station and a fast train moving in front of you. Even you are both on the same location, you cannot jump into the train because of the energy barrier. And this energy barrier goes down, train slowly coming down to a stop. At a small difference, even it is moving, you can jump into. That is the scenario I'm talking about. The velocity between the train and you getting smaller and smaller. Velocity is our case energy. So they get recombined. So I cannot use graphene for create a photo detection normal scheme. So I had to create some clever way of doing something different. And we found a technique like that where we absorb strongly at one end and almost absorb nothing on the other end. And each time you do so, you create thermoelectric voltage across graphene, and that's what you measure. So photon in, voltage out. That's your photo detection. So again, we could make it. You grow. This just appeared this month at Nature, and kind of and press release coming. I think in a couple of weeks time. So I think it will make a lot of information. I think it will be covered by many press. But this is kind of a new. We can actually develop the technique and make pattern. And just I'll just scan through quickly. This is just not so important to understand. But for a scientific standpoint, we spend long time to develop a finite element simulation model to model everything, because it's an expensive process to make work with graphene and make a detector. So what we did, we model everything on a FEM, how the energy being generated, how energy get diffused, carrier diffused, everything in a console, and we predict how the detector will perform. So by saying so, again, that's some of the technique. So the bottom line is we could actually predict the detector performance. The gate voltage means, again, this is a graphene I was mentioning, that if you apply a gate, you change its carrier concentration. So again, if you still know what carrier concentration, on a graphene, if you make a capacitor, apply a voltage across it, you change its carrier concentration. Means you go from a higher state. This is a high carrier concentration when your Fermi level here. Here, no carrier concentration. You go down again, you have higher concentration carrier. So you can create whether it's electron or hole dominated carrier. But point is that you can change this carrier concentration. You can see that more gate voltage apply, I have a higher carrier concentration, I have a more better way of absorbing photons, and now I can create output voltage. So each time photon getting absorbed, I create output voltage, and I want to bias it at a level where it has maximum carrier, so it's around say 1.5 gate voltage. So and then I get maximum voltage output. So then we can experimentally kind of start after we do the simulation model prediction, that's kind of experimentally done, and you can see that this is my detector voltage output as a electrode here, and here I'm measuring voltage output as a function of, in this case, a gate voltage, and which is basically your doping level. So now again, if that not still make too much of a sense, the ultimate slide is that is a selling slide. This is more of a explaining for scientific, but this is a selling slide. So the normal detector, infrared detector, you measure signal divided by the noise, and that is called D star. So that is the parameter we are behind, and we studied that parameter, signal to noise ratio of this detector. Noise when there is no light, you measure the voltage when there is no noise. So basically that is your responsivity, output voltage of the detector for given incident light. This is light power, electrical power, ratio of that gives you the responsivity. And then you measure the noise. Noise means there is no light, you measure the noise, that's called noise power. So now you divide your signal by noise, and you create a new parameter called D star. This is basically simply signal to noise ratio, and you want stronger signal and weaker noise. That is what we are behind. So, and typically a detector should work, an infrared detector should work at 10 to the power 8 to 10 to the power 9 D star. That was the set by performance limit. So that's what kind of we wanted to achieve. But think what we achieved that, and I spoke since my day one, in infrared detector problem is that normal mercury cadmium telluride or indium antimonide based detector need to be cryogenically cooled. So it has to work at 77 Kelvin. So if you still haven't thought, okay, that's not make any statement, but I'm trying to say that all detector you can buy of your spectrometer, this is simply a one component of a spectrometer which we want to develop from scratch. That was the kind of motivation if you missed yesterday's talk. So this is what the system works. So you need a liquid nitrogen duer. And if you want to buy an infrared camera, good camera comes with a liquid nitrogen duer, and that is big problem for most cases. First of all, they are expensive. You always need to be cryogenically cooled. So, but now we found a reverse way of doing thing, that our detector work better at room temperature. So that is a selling point. So you create a detection scheme which works better in opposite sense. Other infrared detector has an opposite trend. It will be like this. You flip the curve like this. So it does better at lower temperature and does very poor at room temperature. So we could flip that thing based on all the mechanism which we can talk about it. Just that is, then we could have simply talked about infrared detection. That could be a 3-day talk, but that was not the point for this time. So we just touching the base that detector is the most crucial component in spectroscopy. So our goal was to develop a detector which can work at the room temperature. That's the room temperature. So that's don't need cryogenic cooling. So that's what kind of we are behind. Again, not going to the all the details, because we'll be running out of time soon. So I'm saying that now we could actually create a detector. Now, how fast your detector can sense something, which is also a big parameter, right? So we want to, because if it is a slow detector, then you cannot do very good spectroscopy. We just spoke about time resolve ultra fast spectroscopy. You cannot do, a detector cannot change. You cannot follow any change quickly enough. So this is a detector we measured around, say, hundreds of a nanosecond. Typically, any detectors are into the microsecond time scale. So because of this one atomic layer, they are much faster compared to any bulk material based detector like mercury cadmium telluride based infrared detectors. So it's much faster than present detection schemes out there. So plan is to do ultra fast detection scheme using this kind of detector, because we are looking at hundreds of a nanosecond kind of response time. So that's what kind of we are. Again, next was our goal was to do imaging with that our own detector. So that is not easy. You know, imaging is a harder problem. So if you never know how a camera works, so you have to create a focal plane array. You have to create array of detector. That's what your cell phone works. So you need to have a array of detector like this. So you have to create a array. So you have array of detectors. So these are the all detectors. So you have to create the array. So this is two-dimensional plane, and you have to create all of them are detectors. So you have to kind of measure voltage of all of them individually. So that's a extremely difficult problem for academic guys, especially because of the electronics. How can you individually read each individual at a time and do raster scan? So you need to have something very complicated electronics called backplane readout circuitry, which can read the voltage of each detector element. So again, we couldn't go up to that level because of the electronics. So what we did, we took a 1 pixel and moved the image around. So that can take image, like that's how you take a selfie, right? Our whole image projects onto that. So what you do, you took a camera, and that's how your image is. That's what it is. You are doing this. Exactly, your image projects on your detector array, and each one of them measure your voltage and to create image, and that's how we plot. But our case, we have only one detector element because of the complex electronics, not easy to go that level. So we took one element and move you across. So keep yourself static and move that one element around to capture the image. You know, that's the other way around, so that just to show the effect. So we move the image around and for one element. So you could actually start taking images with our own detector. But then what also we could show now just brings us back to spectroscopy, because we can change this absorption band. We could actually take image at 8 micron, 10 micron, 12 micron. So these are actually kind of colored infrared image. So infrared, there is no color, but you can imagine that if you add a pseudo color to infrared light, this is a 9 micron, say 10 micron, 11 micron. So you can actually change the color of infrared light because we could change the absorption band of the scheme. So now it's kind of playing a video that this is simply you are taking image, but as a function of wavelength. That's your spectroscopy, right? You are taking an image as a function of wavelength. So that's kind of, but again, infrared domain, that there is nothing like available at this moment. You can only take, for visible domain, we have the even visible camera actually only have a silicon detector, which, silicon detector takes from 400 nanometer all the way to 1 micron, that it integrates, right? But in the silicon detector, we have this filter, RGB filter. So this is my RGB. So in front of 3 pixel, it has a 3 color filter. So actually it frequency resolve it. That's how we could create a colored image in visible camera. But in infrared domain, the problem is that in the 8 to 12 micron band, that's how the infrared imaging works. So it's not easy to have that similar infrared filter to take an image. So typically infrared images are 2 color, like a monochrome, like a black and white image. So infrared domain, always if you Google infrared images, you will see that red and black background. We couldn't create a colored imaging infrared domain. So this is one of that thing we hope that will open up the opportunity to see infrared image colored. But now if you're still not sure what it will have impact, think about in the night, you are in a pitch dark night and taking of your infrared image. So my image will look like a ghost with orange color, and your background, which is the dark outside. That's the image I'll get. But I don't know what is hidden. If you have a phone on your back pocket, its temperature is a little different than your body temperature. So my body emitting 300 Kelvin at 10 micron photon. This is little higher temperature. So it will emit maybe around, say, 8 micron or 7 micron. So my phone emitting 7 micron, I'm emitting 10 micron. Now if you can frequency resolve it, I can know you have a phone hidden or a weapon hidden. That's a key point. So you can actually get more information out with infrared imaging because of the fact now you can frequency resolve it. Again, that's kind of a long path to take a graphene to make a strong absorber, to go from a graphene to detector to make an imaging tool. It's kind of a quite a long path moving forward from material to all the way to a functional device. Many of them kind of appear on top international cover articles. This is Intel wrote about some of our work, that they use some of the technique I was developing in my postdoctoral research. So I didn't get a money because not a patented, but Intel used a technique I developed into their process steps. Again, lots of money need to for funding. So these are all government agencies to fund research. That's kind of National Science Foundation, kind of open-ended research, and then these are all NASA, DARPA is a DoD, Department of Defense, and these are more of U.S. big DoD companies. They make America's all the, not so dominating thing. These are the people who make missiles and fighter crafts and controls the whole world. So these are the two guys, and I'm always funded through them, so I cannot say anything. I think they're good guys, under quotation, but they are the guys who make all the sophisticated planes and the missiles and the bombers. These are the two guys they make. So, but again, that's kind of wrap us down to a new class of detector. What I thought, just to summarize what we did last 2 days, I thought maybe go through in 2 minutes. I'll try to go to 2 minutes, really 2 minutes. So we started with a infrared spectroscopy to understand material, that we need a light source, and the light source goes inside the material. We collect signal back, and then try to look at the signal as a function of wavelength. So started with UV spectroscopy, and the plan is to have a light source, disperse the light using a dispersive medium like a prism or grating, and then using a pinhole, we can actually allow one light to go through at a time. Each light is illuminate the sample at a time, and then you measure the light intensity which coming through the sample. That's how we could actually kind of measure the absorption of that light based on that material as a function of wavelength. And that's kind of a limitation in UVVs, that we have to be high enough energy so that you can excite the electronic states. So these are all electronic absorption. You have to make the material go from balanced state to the conduction band, and you have to make sure that your light energy is enough to give this enough energy. That's what we did. And then we could create a spectrum as a function of wavelength and intensity. And then all kinds of molecules, organic, inorganic, mostly drug design compounds are done through this UV spectroscopy. Basically mapping, send one type of light and measure that intensity and keep changing that light. The problem here, that leads us to a problem, because you need to have a dispersion, means you need many wavelengths to be created before you do the spectroscopy. That brought us back to a more advanced spectroscopy called Fourier transform spectroscopy, where we are measuring the vibration of the molecules, not the electronic transition. So that means we need a smaller longer wavelength or smaller energy. So that's what we did. So we kind of went back to infrared light and excited with infrared light various vibrational modes. And then to overcome the problem of this many wavelength you need, to do so, we introduce a Michelson interferometer, where your light comes through two different paths and interfere on the detector, and do Fourier transformation to that's the interferogram. So your sample seeing interferogram of your own, so x and x plus some delta t, so with some different path length, and you interferogram, you do a Fourier transformation, we get the spectrum back, which all gone through in detail. So again, a lot of application. You are not limited by the wavelength. You can do many wavelengths without being dispersive. So that gives you much more wavelength resolution compared to a normal UV spectroscopy, and wide range of materials can be analyzed, from gas to liquid to solid, of all kinds, liquids from organic to inorganic. Then we went through to show that we could use this spectroscopy in FTIR to identify all kinds of plastics in my lab, just to show that. And even if we add colorants and addend, you can still identify them very accurately, about 100% to 96% accuracy on any random plastic. You can use FTIR spectroscopy to identify them. and you can add some intelligence like artificial intelligence to improve your accuracy of detection. Then we took the same concept to analyze various freshness of the fruits and vegetables, again based on spectral signature, so you can understand where you stand. We further gone through to show that you can analyze organic versus inorganic vegetables, where people add a lot of chemical for the pesticides. You can do all this thing. We also studied avocado to show that what is a good time for the avocado to be ripe enough. So you used to do a ripening study on avocado to find out through spectral response and when it is optimum time for plucking them or even eating them. Next, which is mostly from here, we did some measurement on coffee beans just to show that to understand the coffee quality. So it's very kind of quick scan, and I think need bunch of work to identify what is called quality, which is subjective. But the point is that you can identify the spectral signature of various coffees through the FTIR measurement. Then next we talked about how to build a spectrometer. First we talked about that we may not need a very complex spectrometer, so you can just build a spectrometer based on dispersion again, which is limited. But many times if you want to make a handheld spectrometer or a small footprint spectrometer, you can just use a very simple technique to create that. And then we showed that in the lab, bunch of undergraduate students in my lab, they actually built their own spectrometer in a very small footprint actually. They're very simple, buying few $100 elements, they build their own spectrometer. Next we showed that the key path is that spectrometer is very limited because it does not bring Fourier transform. The resolution is very bad. So this is my FTIR measurement through $350,000 spectrometer, and then we downsample. We cannot collect 3,000 wavelength. So we just collect maybe 100 wavelength and use the artificial neural network to capture the key features. So that is a very downsampled, a low resolution spectrum, 100 sample compared to 3,000 sample, and use a neural network to artificially improve the matching. And we showed that quite good accuracy actually, over 95% accuracy. We can predict all plastic. These are kind of major plastic category, and you can see that each time there are some false detection, few, but majority times we have very good detection accuracy through a very 100 data point. Again, then we kind of introduced this new class of detector where we showed. Then quickly we just spoke about that. That's kind of offshoot that we need a good detector for spectroscopy, and that's we cannot do cryogenic cooling. And then Raman spectroscopy, the plan was today morning we spend time on how to measure the low energy modes. So that's what the Raman spectroscopy does. So it excites with a laser and only one wavelength. It doesn't, unlike the other spectroscopy like FTIR or UVVs, it doesn't use a broadband source. It simply excites with a one narrow wavelength light, and the vibration of the molecule creates those other lights called Stokes and anti-Stokes, which we gone through today morning, and that's we will be detecting. So you just need one narrow line laser, typically a green laser like my laser pointer, and you create all these modes because of the vibrational resonance of your molecule, and that's how it look like. You just you excite your sample with a laser beam, and you collect the light back, all the vibrational modes you generate and collect back. And again, you need to disperse them because your detector don't know what wavelength is measuring. So you have to kind of specially disperse them, your different directions, so that you know which color or which wavelength you are detecting. That's what they do. And then we found that the Raman actually can identify, in this case, ethanol, even in presence of water. This is a pure water, and you can see even if you mix 50% ethanol in water, 20% ethanol in water, but you see the ethanol peak remain unchanged. But there are water peak, but ethanol peak. So the point is that Raman can be used to accurately identify a molecule even in water, which is a good selling point, and all kinds of biological too, organic, inorganic. And then we kind of jumped into a pump probe setup today morning that we are planning to measure the spectrum as a function of wavelength and also as a function of time. So you excite with your probe, pump beam, and create some change, which is maybe generate some carrier, and bring a probe pulse, which as soon as the carrier you generate is reflection from the surface or transmission from the surface changes, and you measure that. So that's what you showed, that you can actually understand. You excite a carrier using a pump laser, and carrier slowly diffuse and dies, and that you can actually measure the pump probe. Next we went to these today's just now, that we could actually use a tip to measure called scanning near field optical spectroscopy microscopy. You can actually use a small tip to really collect signal from a very sub wavelength area, tens of a nanometer, using AFM tip, and that kind of helped us to collect the scattered field from a very small narrow area and allow us to see things which is normal optical spectroscopy doesn't allow us to see, where can resolve tens of a nanometer and even can see how surface plasma propagates, which are typically tens of a nanometer or lower wavelengths. So you can actually measure that using this time resolved. And then further you can actually combine these two. You can actually have a pump probe setup with a tip enhanced and also Fourier transform. So whatever we spoke today, last 3 days, can be combined together into make a combined setup. We just ended before that. You can time resolve it, spatially resolve it because of that tip, and also frequency resolve it because you're doing frequency Fourier transformation. So again, with that, I think I stop and hope some of you got something out of it, and hopefully it will excite you to do better researcher. And if you have more questions, you can always talk. You can always reach out to me. My web page can be reached out. You can see we are always do things for anything experiment you want to do. Always welcome to visit us. We are quite resourceful in terms of making things, which my selling point. So you can always do some actual experimental measurement, and Anna is point of contact. You can always reach out to me and visit us at crossing the Cuba. You have to just cross the Cuba, that's it, and then you are there. So with that, I should stop then. No, I showed 3 days of such a condensed information is not easy. Look, a lot of information need a lot of time. Just one of them we could spend weeks to go through, but that's a long time. So rather get this simply motivate you. It's nothing. I'm sure 3 days, 2.5 hours per day is not enough to cover such a vast field of spectroscopy. So each one of them is so deep. People spend their whole life into that. So you cannot summarize a whole life of work into 7 hours of talk, which is impossible. But it's kind of an overview of the many things people does. Try my best to go touch base the basic principle, but you can always read through. So I can give the PowerPoint slide back to you. You can give it to everybody. There's nothing confidential about it. So general knowledge, you can read through, and yeah, reach out. Most of the thing I talked about, except this one, we have the ability. This one, I think only I'm not sure who has this at this moment. I heard one person at Princeton may have, but nobody has at this moment to really do this kind of very complex spectroscopy. So this is, apart from that one, most of the thing I spoke about, we have a ready-made solution. If you have a sample, we can always measure for you quickly. So that's the point. So.